Hey everybody, welcome back to another devlog of sharks and alpacas, I guess. My Python game development project using pygame. And last episode we introduced the concept of roaming around animals, namely alpacas of course. And another thing I want to implement in the future is placement of objects that are persistent and entities in the environment can interact with. But before we start on that, I want to change the orthogonal tiles we're using right now and use hexagons instead, a hexagonal grid, because hexagons are bestagons, of course. However, this will introduce a lot of complications for algorithms I already implemented for the square tiles. It's gonna be a challenge, but it's one I'm looking forward to. I was already playing around with the hexagonal coordinate system a bit last week outside of the actual game project. And this is a little Jupyter notebook I've been working in, and here you can get an idea of what this will look like. So we have a whole hexagonal tile set, and already I think from this you can see that it will look a lot more interesting. And then we of course have a zoom in where we can see the camera cutout of the whole world. And what I was working on here is, if I give it a random coordinate in pixel coordinates, how can I determine which hexagon this coordinate lies in? And that brings us to one of the core problems now. It's not that easy anymore to convert from pixel coordinates into tile coordinates. But let's have a closer look at that in an actual pygame run, because I implemented exactly this in a little pygame window here, and you can see we can move around and it always will find the hexagon we are in. And on the top left you'll see 3 coordinates instead of 2 that we normally had, and those are so-called cube coordinates. It basically is the coordinates along 3 axes along the different hexagonal lines. So what you have to do now is you have to convert between the pixel coordinates in x, y. You have to consider the hexagon IDs that are used to draw the different lines of hexagons, and you have to know the cube coordinates along every axis of the hexagons, because this will make it much easier to do different math, like for example finding your neighbors or the next neighbors or any arbitrary distance along this coordinate system. And this is things I all figured out more or less in the beginning by myself, and then I found a really great documentation. I'll link it in the description for you guys to check out. That has a lot of the info I was looking for and some pseudocode that was ready to be implemented right away, and that helped a lot. So one concern was for me to not render more than I have to. We had this problem before with the camera. If I render all the tiles off camera, we had a huge drop in frame rate. So one thing I wanted to figure out before I try implementing this in the game is how can I determine which hexagons to render. And if we start this again with a bit of padding, you can see exactly what's happening here. I only render the hexagons that are overlapping or a little bit of buffer to the edge of the screen. And this helps with the performance no matter how big the world is. Alright, that was a long introduction. I hope you are as excited about this as I am. I think it's gonna look really good with the islands in a hexagonal coordinate system. So let's get this working in the game. I started working on this conversion on Sunday afternoon. Now it is Monday morning and I made a bit more progress. So after a few iterations, I got at least the tile code working fairly quickly. So that shows that the tile code was fairly modular and flexible. However, now I struggled for quite a while getting the mouse orientation right, and it seems to work now. However, when I use the zoom, things are still very much broken, as you can see. Oh no, poor character being dismembered. But yeah, the gameplay. The tiles are still not recognized properly. Sharks can swim on the land, and I cannot walk everywhere on the land, so that is something I'll have to tackle next. Bear with me, this is going to be a slow but steady progress. Trees are back and items are back too, and luckily those are all based on coordinates, so no reason to worry about those. Anyways, things are slowly coming together and it almost looks like the game again, doesn't it? One of the things I'm still a bit worried about is the reflection. We have the sharks reflecting off the land tiles, we have the alpacas reflecting off the water tiles. Previously that was quite simple because it either happened on a vertical or horizontal line, so I could just invert the vertical or horizontal speed of the object. Now there's diagonal lines, which I have not implemented yet, so this is going to be one of the challenges. But I'm sure with a bit of tinkering we can figure this out as well. I've been playing around with it a little bit again in my little Jupyter notebook here with the hexagon tile experiment, and as you can see I was able to implement a movement vector. Right now I control it with the mouse, but eventually it will be controlled by the movement, and I can detect the intersection to the neighboring hexagon, and if the speed is small enough to stay within the same hexagon, there will not be any intersection. The way I do it is quite simple. I project the target coordinate of the next frame, and if it falls within another hexagon, I determine the intersection of the corner points of the neighboring hexagons, and then using the normals of this line, I can make the reflected vector, simply like this. And of course I had to look it up. I did not just figure this out by myself, but it is rather simple once you know how to do it. So this works really well, with the exception of some special cases. If the velocity is high enough or the frame rate is low enough, the target coordinates might actually fall beyond the neighboring hexagon, which leaves you without any intersection. And right now I deal with it by limiting the maximum velocity. But in the game this might not always be controllable. And look at this. You can see that the intersection should still be on the right side, but because the target coordinates end up in the hexagon below, it finds the wrong side of the hexagon. The day passed and I kept thinking about it every now and then, and I think I came up with some sort of a solution. So this part of the code here is what calculates the reflection of the line, which is the edge of the hexagon. And with only one additional dot product here, I can actually calculate the intersection between the vector and the edge of the hexagon. Now I have the reflected vector not start at my position but at the intersection point. Here it is outside of the line, and if that is the case I can simply use this intersection point to determine the hexagon that this intersection point lies in, and then use that edge instead. But that still leaves us with this problem here. So even with a limited range, I can still reach the next hexagon. So what I'm thinking about doing is, if it is the case that there are no intersections between the target hexagon and the current hexagon, I will truncate the vector to one side length of the hexagon and then see where it lands. This should always give me the right result. So let me implement these fixes and then we're going to test some more edge cases here. You know what? Let's lay it out clearly on a case-by-case basis, because this was all very convoluted. The most common case in the game will be that the target will be within the same square as the start. Because we have a high frame rate, we have relatively small velocities. The second most common case will be just a normal reflection, which means that our target will be in a neighboring hexagon. We will find our 2-point intersection and we can simply reflect from that. Now let's go to the more rare cases. Number one is what I tried to show earlier, where we basically skip an edge of the hexagon and land on the wrong one. This we can solve with the intersection. And then number 4 is the case where our velocity vector is so large that we'll skip a hexagon. Let's clearly outline the criteria for each case. Case number 1, the target hexagon ID is equal to the player hexagon ID. Case number 2. The target hexagon and the player hexagon have an overlap of exactly 2 points, and, importantly, the intersection of the velocity vector and this line lies within these 2 points. If that is not the case, we'll fall into case number 3. And then finally, if we don't find any intersection points between the target hexagon and the player hexagon, we truncate the vector to one side length of the hexagon, and if the target is then the same as the player hexagon, we add another side length to the vector to make sure it reaches the next closest hexagon, and then we go back in the loop and find the 2 overlapping points of these hexagons. And I think this should cover all our bases, and we should not run into any unexpected situations in the game. I realize this is quite the abstract video compared to the previous ones, but you know what? These little challenges is exactly why I enjoy this project so much. And just after saying this, I spent 2 days dealing with some more unexpected challenges, but I'll talk more about raycasting and hexagonal grids in the next devlog, which means there will be a part 2 of the hexagonal conversion. But I hope you enjoyed it anyways, and I hope to see you all again in the next devlog.